In the previous video, we discussed this concept of how to create a buffer from a basic recipe. And we said, this should not be a problem. I should be able to give you these types of questions as long as I give you the volume that you need to make and the concentration of the acid and the base that's needed to make the buffer. Then you should be able to use the molarity equation, or you should be able to use another concentration equation that we've used before in the past to figure out how much to weigh out. These are the things that you do all the time in the lab. If they give you a concentration, you got to calculate how many grams or how many milliliters to use. That's what these questions are all about. But I also told you that these were the basic buffer questions, that they can become a little bit more complicated. So what other types of buffer questions could I expect to see? Well, first off, we said that we pick out a weak acid and a weak base combination in order to make a buffer. And if you noticed in the last example, I told you what that weak acid and weak base was going to be. So sometimes it's up to us to choose the proper weak acid and the weak base to make our buffer with. Now, why would I need to choose a proper weak acid and a proper weak base? And the reason is that sometimes the labs will be very vague, and they will not tell you the exact recipe that you need to make. Or maybe you're working on a new test or a new method that says you need to prepare a buffer, and this is the buffer that you will need to use for the experiment to work out the proper way. So how do I pick out the proper one? All the acids that are out there, all the bases that are out there, how do I know to pick out the proper one from the list? Well, chances are it will be very vague, but they will at least give you a pH target, meaning that these questions might say, hey, you need to make a buffer, and the buffer needs to be around a pH of a 4. What weak acid and what weak base would you choose in order to make this buffer with? Right? That could be what they're after. So how on earth do we do this? Well, this is pH dependent, right? It's telling me the buffer has to be relevant in the pH of 4 range. So that means when I go and pick out my weak acid and base combos, I don't want to pick out ones that will make a buffer that has a pH of 8, right? That's stupid, because it's only going to buffer in that pH range, meaning that when this buffer is made and that buffer's pH is 8, if I add acid or base to that solution, it's going to keep that solution around a pH of 8. And maybe that's not what this experiment wants. What this experiment wants is a pH of 4, not a pH of 8, meaning that pH of 4 has to stay pretty constant throughout the entire experiment. If not, then this experiment could go bad. One of the first things that you will see in a working laboratory are reactions that are pH dependent in organic chemistry. And sometimes these things get very explosive. Sometimes these will catch on fire if they are outside of the workable pH range. So I have to make sure that buffers are in place to take care of this. I need it to be pH of 4. I don't need it to deviate too much from pH of 4. So what on earth do I pick in order to make that buffer with? Well, one of the very first things that you look for is the pKa of the acids. If you've got a general chemistry textbook, flip it to the back. You're probably going to see a whole appendix that will list tons of different acids for you. And those acids will all have a Ka value or a pKa value. Now remember, if your table gives you a Ka value, what you need to do is take the negative log of that number, and that will give me the pKa. That's the number that we need to focus on, is the pKa number, not the Ka number. So I need to look for pKa of acids. And what I do is I want to choose one of the acids that's plus or minus 1 from the expected pH range. or the pH of the buffer. All right, so for instance, if I've got to make a buffer that has a pH of 4 that should keep something around a pH of 4, then I need to choose the proper weak acid and base. So I'm going to go to that list, and I'm going to scour through the list until I find a pKa value that is around a 3, 4, or 5. That's plus or minus 1, right? A 3, 4, or 5. And when I find that weak acid, then that is a proper weak acid to use. Well, you know what? If I go through and find acetic acid, that's the acid we used in the last example, my pKa for acetic acid is 4.76. You know, that's pretty good. I mean, that's pretty close. I'm not going to find anything that's going to be perfect sometimes. As long as I'm plus or minus 1, then I'm okay. So acetic acid, pKa 4.76. This makes a great weak acid to choose when making the buffer. All right, so what about the base? Well, if this is acetic, I now know that I probably need the acetate from the acetic acid, and I probably will put sodium out in front of it, and that will be my weak base that I need in order to make this buffer. Now, sometimes this is only a part of the problem. The part of the problem will be to pick out the right combo. Go through a list of acids. They could give you those lists of acids. They could make you refer to a list. You're probably going to find a document in Blackboard that you can download with all of these Ka and pKa values on it. So that way you get very familiar with the acids that are out there and their values that are associated with them. So this would be the first part of the question. Pick out the proper one, and then once you pick out the proper one, pick out a proper base that corresponds to that, and you've answered that part of the question. Now, the next part of the question would be something like, okay, well, if you have to make it have a pH of exactly 4, then what would you use? How much of each one of these, right? Because acetic acid has a pK of 4.76, not 4. It's within plus or minus 1, though, which is a proper acid to use. But what if we have to be very specific on the pH value? What if we really do have to make a buffer that's exactly 4.00 pH? How do I do it? Well, that's going to be the second part to these questions. Now that you've chosen your acid and now that you've chosen your proper base, how can you mix these together? In what ratio? In what proportion? How much of the acid, how much of the base do you need in order to make this thing have a pH of 4.00? And let's say that I need 250 mils of the buffer in total. How on earth do I do this? Right? Well, that's where an equation is going to come into play. And this equation you need to know, meaning that it will not be given to you on any type of test or any type of exam. All right? We need to know this equation that I'm getting ready to write down. So you might as well go ahead, write it in your notebook, memorize it, make sure that you understand where all of the variables go and what they mean. So this is going to be called the Henderson Hasselbalch equation. And this is specifically to make buffers. That's why we would use this for the most part. All right? So in order to use this equation, what does this equation look like? Well, this equation says pH is equal to the pKa. So the pH of the solution that you're after is equal to the pKa of the acid that you have chosen. And that's going to be log of the base over the acid. Now, I should say that should be a plus. Plus the log of base over the acid. All right, so this is the Henderson-Hasselbalch equation. Now, this base and acid, these are in terms of concentration here. And concentration is specifically given most of the time in molarity. That's typically how we would use these. It's typically what we would see. That's kind of how the equation is written. That's how it's interpreted, and that's how it's used most of the time. So molarity would be the concentrations that would go into this picture. So pH is equal to the pKa plus the log of the concentration of base over the concentration of the acid. So this is what we would call the HH equation. That's how I abbreviate that, HH. I'm too lazy to write down Henderson. I'm too lazy to write down Hasselbalch, right? So HH is going to be the abbreviation. So the pH here of this solution that we want to make is a 4. So 4 is equal to the pKa of the weak acid that I've chosen. Remember, that was 4.76. We said that we were going to choose the acetic acid, and acetic acid had a pKa of 4.76. It's plus or minus 1 of the target pH that we want to make. Okay, so plus log of the concentration of the base over the concentration of the acid. And you know, I'm going to erase this for a second because I used B for base. Most of the time, though, in a general chemistry class, they will use the A minus for the base just to keep this thing kind of consistent. So A minus and HA. So if I can kind of solve for this ratio will give me an idea of how much I need of one compared to the other. And that's really why we're using this equation. I need to figure out amounts, right? I've got two different things. I need to put both of these things into the same flask. I need to make sure that when I mix these two things, they give me the proper pH. And I'm after that ratio. I want to know how much of one over the other one. So in order to do this, this is 4.76 plus log of A over HA. So I can subtract 4.76 from each side. When I do that, I'm going to get a negative 0.76 is equal to the log of A over HA. And I need to basically solve this example or solve this equation and get this ratio by itself. So I've got to get rid of this log in a way. How do I get rid of the log? I do the inverse log. So to solve this next step of the equation, I need to do the inverse log, right? So the way that we do inverse log is we take 10 to the whatever that number is supposed to be. So this is going to be 10 to the negative 0.76 is equal to 10 to the log of that. So that just kind of cancels each other out. And what I'm left with is A minus over HA. A minus, again, is the concentration of the base divided by HA, which is the concentration of the acid. So I need to bring up the calculator, and I'm going to type in 10 to the negative 0.76. And the way this calculator is made, I actually have to put the exponent in first. So 0.76, there's my negative 0.76, and I'm going to hit 10 to the x right up here. If you're using your scientific calculator, you'll probably need to put that in first, 10 to the, and then put parentheses, negative 0.76, close the parentheses out, and then hit enter. So you should get around 0.173 or 174 on your scientific calculator if you do it that way. Again, it's just the way that this calculator is made. I had to do it a little backward. So 10 to the negative 0.76. That's the way that it should look like in your TI 83 or 84 or whatever you're deciding to use, okay? So 0.174. I'm going to round that off to 3 digits, 0.174. So the ratio here is 0.174. And that's equal to the concentration of my base divided by the concentration of my acid. So this is a way that we can maybe figure out a ratio, how much of one to how much of the other, in order for this to work, okay? So if I kind of step back and I think about these numbers and where they lie, here is pH of 4.00. This is acidic, right? And then 4.76 is the pKa of this acid, and 4.76 is a little bit higher than where I want to be. So as far as my base is concerned, I don't want to put more base in there, right? If I put more base in that solution, then it's going to make me have a pH greater than 4. So I need more acid than I need base, which is why this number is so much smaller, 0.174, right? If this was a pH of a 5, then this 5 number is greater than the pKa of the acid, which means I need to be more on the basic side, and I need more base than I do acid, and for that reason, this ratio might be greater than 1. The ratio will be a much larger number than what it is now. So just kind of look at your numbers, try to gauge where you are in the process to see if it actually starts to make sense. So there's the ratio, and that might be one part of the question, but I'm not done because I need to figure out how much of each one of these that I need to use to make this solution with, right? Okay, so I'm going to erase this top part. And part of the question that I've not given you yet, there's always a tidbit piece of information in there that confuses people. And it's this total amount of ion. What is the total amount of ion that I should be using to make this solution? And the reason is because it doesn't really fall into play until right now. Okay? And this is the reason why we always have to talk about this. When you make a buffer, you are adding a certain amount of acid and you're adding a certain amount of base into a flask, right? Well, for the buffer, it's going to use this weak acid and weak base to neutralize things. And we've talked about that already. But once the weak acid and weak base is used up, then it cannot do its job anymore. And my pH is going to drastically change. So if I add an extra little drop of reagent and I think that my buffer is going to hold it at pH of 4, and that extra drop just really sends it through the roof, and now my pH goes from a 4 to a 6. Well, this is called buffer capacity. And if you use a little bit of common sense, what you would realize is that the more weak acid and the more weak base that I add into this flask, the more reagent it can take before my pH decides to change on me. So they're always going to have to give me a little tidbit of information. How strong should this buffer be overall? Right? That's really what we're after. So what we've done in the first part is that we've picked out the proper acid-base combo. This is kind of proper. This is where we need to go. This is what I'll pull from. And now I have what we call this ratio of the base to the acid. I know kind of the recipe at this point, right? The problem is that I just don't know how much to make. Here I've got my ingredients to make the cake, but how many cakes do I have to make? That's really what we're after now, right? Do I just need to make one, or do I need to make 15 cakes? Because if so, then that's going to change how much acid and how much base that I need to use, as long as it's in the proper ratio down here at the bottom. So they always have to tell me the total. So in this problem, what they would have done is that they would have said your total acetate concentration would probably need to be, who knows, 2 molar, 0.2 molar. So how much acetic acid and how much sodium acetate do I need to use in order to make this strength of buffer? They think that if it's 0.2 molar, it has enough weak acid and base in it to do its job pretty well, and that you should not see a pH change involved in the reaction if you use it. So I need to now go through the next step. I'm going to come over here to the side and I'm going to write my ratio here. My ratio was 0.174, and again, this is my base to the acid. Okay, so now I'm going to erase all of this other, because we need to continue on with this Henderson Hasselbalch equation and calculation to figure out how much exactly of each one of these do I need. All right, so here I've got two different variables, and I can kind of come up with two different equations in order to solve for these variables, right? Only thing I want to do is down here to the side, I want to actually give you a algebraic kind of form of what we're after here. So total acetate has to be 0.2, right? So that means the concentration of the base, sodium acetate, plus the concentration of the acid, which was acetic acid, both of those carry the acetate ion, have to add up to be 0.2 molar, right? And then up here at the top, we know that the concentration of the base divided by the concentration of the acid has to be 0.174. This is kind of the take-home equation that I need to use, and this is my second take-home equation I need to use as well. I need to understand what is the total concentration that I'm after. And in this example, it would have told me 0.2, right? And hopefully all the other example problems that you'll work will also give you an idea of the concentration range. It's kind of like solving for molarity. How would you know how to solve for molarity if they didn't tell you the other two pieces of the puzzle? How much of it do you need to make, or how many grams did you weigh out, or what target concentration are you after? That's what's happening here in this problem. So typically what I do for the next step is that we've got to get this equation and this equation talking apples to apples, right? And right now I have this acid and base, and I've got this acid and base, and I need to pick one of these equations. I'm going to pick number 2, and I'm going to solve it for the base. That's just typically how I do these problems every time. So if I'm going to solve for the base, I would take 0.20 minus the concentration of the acid. All right, now I'm going to kind of redefine everything that I'm using here. I'm going to say my acid is equal to the variable of x. And I'm just going to rewrite this. So the concentration of the base is equal to 0.20 minus x. So here's my first equation, right? All right, well, up here's the other equation, my ratio. My ratio was 0.174. And that's equal to the concentration of base over the concentration of acid. Now look what I can do. My ratio is 0.174 equals the concentration of the base. I don't know what that should be, right? But I've just solved this second piece of the equation, 0.20 minus x. And then the concentration of the acid, I said my acid is equal to the x variable, so x is going to go there. Now all of a sudden I've got this algebra equation that I can solve a little bit better here. So I'm going to multiply each side by x, and that gives me 0.174x is equal to 0.20 minus x. Then I'm going to add x to each side, and this gives me 1.174x is equal to 0.20. And then to solve for x, I'm going to divide by 1.174. So if I bring up my calculator, I'm going to take 0.2, which is the total amount of acetate that I should have, divide it by this 1.174, and I'm going to get 0.170. And this gives me the answer in molarity, and this is my x number, kind of, right? So there's my x. My x represents the acid concentration, so this is the concentration of the acid. Now, if I need the concentration of the base, what I would then do is that I would take 0.20 and I would subtract x from it, which is 0.170. And then when I do this, you can not probably do that without using the calculator, but I'm going to bring it up anyway. So 0.2 minus 0.170, and I hit enter, and I get 0.03. So 0.030 would be the molarity of the base. Okay, so this is going to tell me the concentrations that I need of each one, the concentration of the acid and the concentration of the base. Now, if the problem gives me the total volume that I need to make, then I can take this molarity, plug it into the molarity problem, moles over liter, solve for mole, multiply by formula weight, and that will tell me the amount of base I need to weigh out on a balance. Okay, the same thing would happen with the acid. acid down here at the bottom, if I know the strength that I should end up with, and I know how much in total I need to make, then I can plug this into the molarity equation, solve for mole, multiply by formula weight, and that will tell me the amount of gram of acid that I need to weigh out in order for this buffer to work. Okay, so this is a nightmare, right? And no one said that buffers were very easy. But this is an example of one of the most complicated type of buffer problems that you might see in a laboratory. And the problem here is that the directions are not very direct, okay? They're letting you know, hey, we need to make a buffer and it needs to be this pH range. What would you pick? And then once you pick those, hey, you know, we want this pH to be in this range. What's the ratio of acid to base that you need to use? Well, we solved for that. And then it pushes you to the next step. And now it says, hey, since you know this ratio, now let's figure out how much acid and base to actually measure out in order to make the buffer. The problem, though, is that somewhere they're going to have to give you the total amount of ion, and in this case it was acetate. So how much or how strong do I need to make this buffer? That way we can ensure that this buffer is going to cushion my pH for me if it goes slightly acidic or slightly basic. It's not going to go over the buffer capacity, and then all of a sudden it's like, why did I make the buffer in the first place? If my buffer capacity is really low and my buffer is not going to do the job, then why did I take all the trouble in making this buffer if it's not going to keep the pH at a certain range for me? Okay, so this kind of finishes up this example problem, and what you're going to find out is that in the other parts of the lecture module, these are going to be YouTube videos that are probably going to come from other people that's going to show you different types of buffer problems and how they would work out these types of questions using the Henderson-Hasselbalch equation. Right? I just gave you one example, and I gave you the most complicated example. However, there's other pieces of the puzzle that they could give us to make this process so much better, and I'm going to let them kind of explain to you how to solve that Henderson-Hasselbalch equation accordingly, and how much easier this process could get. But if you've got questions, you know how to get a hold of me. So from here, I'm going to turn it over to other people. I'm just going to kind of let them walk you through solving these example problems. And hopefully you'll have enough by the end of this to solve these problems on your own in the very last assignment that you will see in the course.